So now we're going to talk about conductors and equilibrium. Now this video is a little less mathy than some of them, so I apologize, but don't worry, when we get to Gauss's law there'll be plenty to go around. So in this video we're going to talk about properties of conductors in general, and then we're also going to define this term called electrostatic equilibrium. Spoiler alert, it's exactly like equilibrium from first semester, except your force is caused by the Coulomb force. Let's talk about some of the basic things you need to know. First off, using the definition of a conductor, your electrons are free to move around. So they're not tied, they can just go wherever they feel like. The second thing to know is your electrons move to cancel out E fields. So when we talked about the electric field, we talked about the electric field was equal to the force over Q, force per charge. Since force is a vector, if your electric field is not zero, if electric field is not equal to zero, then your charge feels a force. So going back to first semester in Newton's second law, you know that the sum of forces equals mass times acceleration. So therefore, if there's no electric field in a conductor, there's no force, there's no acceleration, and your equilibrium condition is met, which is net force on the charge is equal to zero. So pretty much what's going to happen, all of your charges are going to move around until the electric field's zero and they're not accelerated and they just sit there. They're in equilibrium because they're not accelerating. So the first property, let's say you have two charges that are real close together. Now if they feel an electric field, they're going to react, as we mentioned earlier, F equals QE, which means they're going to feel a force. In this case it's going to be repulsive, and these two charges are going to repel. And what's going to happen is that all of these charges are going to distribute themselves so they don't feel any electric field. Right? Because if there wasn't a net electric field, which you can calculate by superposition, these charges would move. So in a conductor, E equals 0 inside a conductor. Now the second property says that any excess charge is going to be on the surface. So where do these charges go? As you get farther away, what happens to the electric field? Right, so the farthest the charges can get away if they're confined to this conductor is on the surface. So all of the charges will reside on the surface of this conductor, just because they're trying to get away from each other. This rule is a little harder to see. The electric field on the conductor is perpendicular to surface, but if you think about it, what happens if the field was left or right? Okay, in this case, left or right. So if the field went this way or this way, this charge right here would go, and then it would move all around. So the only way that the electric field can go and not move a charge is perpendicular to the surface. So the electric field coming out this conductor is perpendicular to the surface everywhere. And the reason for this is because if the electric field was not perpendicular, and if it went left or right, these charges would move around and there'd be a force, you wouldn't be in electrostatic equilibrium anymore. So our final rule is that if you have an irregularly shaped object, charge accumulates at the smallest radius of curvature. We would call these the sharp spots. So if you look, all the charges on the surface, and we've got this little teardrop shape. Well, if all the charges on the surface and they're moving away, you can see that your surface gets kind of clumped together right here. Now we will verify this numerically when we start talking about potential, which is going to be in the next couple chapters. What we can do with this, again, guy named Ben Franklin, remember him, we talked about him. If you have a house and you put a little lightning rod on top, you get a high electric field. Let's make this a little more teardroppy. You get a high electric field on the point so that lightning, you get an electric field, goes to this lightning rod. And then your house is saved and everybody is happy. Now let's talk about how you can use this. You fly in a giant metal tin can, and it's going through some storms. Then all of a sudden, lightning strikes. But if you notice, the people inside aren't fried. All right, this happens quite a few times, and it can happen a lot. But the people inside don't really notice. Why? What's the plane made out of? All right, so if we look at this plane and we model it as a conductor, because it's metal, this is a block plane, I assure you it's just as good, the charge resides on the outside. All right. Same thing happens if a power cable hits a car. The car is a metal cage. All right, and they call this a Faraday cage. A Faraday cage named after. And since the people are inside this conductor and the charge is on the outside, everyone's going to be okay. And then if you wait long enough, this charge is going to dissipate back to the air, back to the clouds, and it'll eventually just transfer somewhere else. So let's talk about what happens if you put a charge, Q, I'm going to call this plus Q, inside a conductor, or a conducting shell. So here's my conducting shell. Where does all the charge reside on this object? Is the charge stationary? No. So what this means, you've got a plus in the middle, your minus charges come to the side, your positive charges stay on the outside of the conductor, so if we said Q inner surface, well, this would just be equal minus Q, and Q outer surface equals plus Q, because that's the charge that left. The charge, negative charge, came to the middle to cancel out this electric field caused by this Q in the center, leaving the positive charge on the outside. So to an outside observer, someone way over here, all they see is a box with Q. It doesn't matter if it's a circle, it doesn't matter what exactly it looks like. Your inner surface will always have minus Q, your outer surface will always have plus Q. Now I'm going to put up a link to the Architect video. Architect, they have fun with Tesla coils and Faraday cages. It's really fun to look at. Don't try at home. Don't try at home. So just to wrap this up, we have electric field is 0 everywhere in a conductor. All excess charges on the surface, the E field is perpendicular to the surface, and you have a stronger electric field at the sharp points. Hope this helps.